Thank you for joining us today for our webinar brought to you by Converting Quarterly Magazine, the official publication of the Association for Roll-to-Roll Converters. My name is Jeff Peterson with Converting Quarterly, and today's webinar is sponsored by GEW, who designs and manufactures ARC, UV LED, and excimer curing systems for printing, coating, and converting applications. Our speaker today is Jennifer Heathcote. Jennifer is the Vice President of Business Development for GEW, and Jennifer will be discussing UV Hotmelt, a sustainable solution for PSA tapes, packaging, and industrial goods. Before we get started and I introduce Jennifer, just wanted to remind everyone that you are on mute, and if you're interested in asking Jennifer a question, there's a little question mark down at the bottom of your page that you can click and write in your questions. And at the end of the presentation, we'll discuss those with Jennifer, and she can answer them when she's done with the full presentation. So without further ado, I am going to go ahead and introduce Jennifer. It's up over to you.
Thank you, Jeff. Welcome, everybody. We're going to talk about UV acrylic hot melt. This webinar is kind of broken into thirds. I'm going to give an overview on sustainability. It's kind of the way I view sustainability. Sustainability is a construct. It means different things for different people. So I think it's important when talking about sustainability to make sure that the people that are talking kind of give you an idea of where they stand, because it doesn't mean the same thing to everybody. And then I'm going to talk a little bit about pressure sensitive adhesives and how what can be done to make them more sustainable and how they build into maybe that first third of the presentation. And then I'm going to finish up talking about UV technology and how you would match a UV curing system to a UV hot melt application. So obviously sustainability as a term did not exist in 1700 Europe, but the concept of sustainability is probably present in almost any point in time in history where a key critical resource was rapidly being depleted. I pick 1700 Europe because it's the early modern period, and I think a lot of us can relate to it. So if you think back to that time period, wood was the primary building material. It was the primary source of fuel. It was used for shipbuilding, for carriages. It was a very popular material. In fact, every ship in the English Navy required about 4,000 oak trees per ship. And I think they had about, at any given time, they had about 300 ships. So you can imagine if you're using wood from your forest for just about every need that you couldn't use stone, you can imagine that that wood as a resource quickly became depleted. And if we just look at these maps that show the deforestation from about 1000 BC up until approaching 1900, you could see how the trees just they became depleted because they were being cut down to build ships and carriages and all sorts of things, and to heat homes and cook food. And so societies, when this happened, societies start to realize, that the population, society as we know it, can completely collapse if you've got an overstressed environment. And certainly at that time, they didn't have charcoal, they didn't have coal, they didn't have natural gas, they didn't have oil. I mean, it was trees. And so as you had scarcity, then you had to go further away. So you had to sail those ships off to other countries, to the New World, to bring back more trees. And it's kind of this never-ending cycle. And the idea is if you ran out of trees, then society would potentially collapse. But the other aspect of it is that when you have scarcity, it drives up prices. So while those in business may have been able to afford an additional ship because they were trading and bringing goods back for sale, when you put constraints on materials, whether it's through regulation, whether it's through scarcity, just diminished supply, that drives up prices. And unfortunately, you end up in a situation where the most vulnerable often struggle to survive. And that could be the poor, the elderly, but it can also be the lower middle class, the middle class, and increasingly the upper middle class if it's not handled correctly. So to me, concepts of sustainability is how do we protect the environment and preserve resources for the future which I think a lot of sustainability is wrapped up into that. But I think we also have to be cognizant that we want to make sure that we're not impoverishing large groups of society, penalizing smaller businesses that can't comply with the regulatory burdens, starving innovation, and causing vast deindustrialization. And unfortunately, I think a lot of what we are doing in the name of sustainability is causing just that. It's driving up prices. It's making things very unaffordable. And so I think we need to balance this. And I think the pendulum has been so far one way that it's just sustainability for the sake of sustainability. And here's the items you have to tick, and you go away as a business and you implement those without a lot of thought, because we're being told that that's how you become sustainable. And I think the pendulum needs to come back a little bit further. And you are seeing pushback because right now, I mean, there was a poll that was done in 2023, and it was a combination between University of Chicago and the AP, and they found that nearly 2/3 of Americans are unwilling to pay any amount for climate change, any amount. Now, if you ask them if climate change is necessary, most of the, addressing climate change is necessary, most will say yes, but then they're not willing to pay for it. So if your sustainability initiatives are driving up the cost of products, making resources unavailable, you're going to start to get a lot of pushback from your customers, and they'll make choices. And I think we just need to wrap all of this together in the conversation. And what we need to be looking at is processes that can be done more efficiently, that use less energy, that still allow us to make the products that all of us are making within our organizations that we work for. So let's take a look at kind of the timeline of key sustainability policy. I think when a lot of people get into sustainability, they kind of maybe look 5 years back, and they kind of latch on to what they're seeing in the journal articles, what they're seeing in webinars, what they're hearing at conferences. But I think to properly understand it, you kind of have to go back in time. And I just happened to pick 1963. I could have gone back further, but we only have an hour, and I'm only going to hit the key points. So if you look at 1963, that's when the US passed the Clean Air Act. And it was primarily to address air pollution. It was, carbon monoxide, it was ground level ozone, particulate matter, sulfur dioxide, nitrogen oxides, lead. It wasn't the first. You can actually go back to the 1950s, and the UK and the US had passed legislation that primarily had to do with smoke and burning things in urban environments. So really, clean air policy dates back to the 50s. But once the Clean Air Act was passed in the 60s, and then amended in the 70s, and then again the 90s, there was a lot more attention by businesses, I think, for the first time to deal with the effects of how they were operating, right? So nobody wanted acid rain, nobody wanted, smog, nobody wanted asthma. And so there were technologies that were being developed to address that. In 1987, the UN decided to change its mission from being a peacekeeper to being a sustainability champion. So really, it was in the 80s that the environmental movement really got hijacked by climate change and sustainability. And if you look at all the policies since it's come out of the UN, it really has everything to do with sustainability. And 1987 was about the time that word was first coined. In 1997, the UN hosted a conference where the Kyoto Protocol was published. And that was when the UN decided that in order to be sustainable, we had to reduce greenhouse gases. So greenhouse gases are the metric that the UN uses for sustainability. And most of their sustainable development goals kind of hinge around greenhouse gases. Coming out of the Kyoto Protocol, there were two NGOs that partnered up that decided that, well, if greenhouse gases are the metric, we have to have a way to measure it. So the Greenhouse Gas Protocol is a separate NGO. It's supported by the UN, but it is separate. And it's basically an accounting standard. And in 2004, that is when Scope 1 and Scope 2 emissions were established. And I think that's surprising for a lot of people, particularly if you've only heard about scope emissions in the past few years. And I'll explain in the next slide why that is. But they date back to 2004. In 2006, the UN had been coming up with the concept of environmental and social governance. But when they started using it for the first time in policy papers was 2006. And again, I think that's a term that people think is a little bit more recent, but it's nearly 20 years old. and actually is based on discussions and evolving policy that date back and yet another 10, 15 years before that. In 2006, the UN created yet another NGO called the Principles for Responsible Investment, and they launched the principles at the New York Stock Exchange, and it was all predicated on moving environmental social governance into the financial markets. In other words, if you're an institutional asset manager or a financial banker, you needed to make your decisions based on the key concepts of ESG. And so that's when the banks started making decisions on who they were going to loan money to and who, asset managers were going to keep in a portfolio of investments. And that could be, your 401k, your IRA, any sort of investment portfolio that you or your company is investing in. So in 2011, the Greenhouse Gas Protocol comes back and they define Scope 3 emissions. And for those of you who aren't familiar with Scope 1, 2, and 3, I'll explain that on the next slide. 2015 is when the Paris Agreement decides to restrict global warming to less than 2 degrees C and make economies net zero by 2050. They also came out with their 17 Sustainable Development Goals. 2019, the UK becomes the first country to pledge net zero by 2050 and requires reporting of Scope 1 and 2 in financial reports. So again, that's only 2019. And I think that's why in the last 5 years, we've been hearing about a lot of this Scope 1, 2, and 3 is because it's starting to be rolled up into financial reporting. In 2022, the EU requires reporting for Scope 1, 2, and 3 in financial reports. It's called the CSRD. So in the UK, it affects about 11,000 companies. In the EU, it affects about 50,000 companies. The US tried to do the same thing through the SEC, requiring Scope 1 and 2. It would have only impacted about 2,500 companies, but it was immediately, lawsuits were immediately filed, and it went immediately under judicial review because it's not constitutional. So it's kind of hung up in limbo right now and has not gone into effect. They haven't ended it, but the SEC has decided not to pursue any legal defense, probably waiting for an administration that might be more supportive of it. I think it's important to note, though, that we're starting to get a lot of pushback, not just in the US, but also in the EU on this financial reporting. In fact, just last Friday, it was the 10th, there were, I think it was 46 CEOs in Europe are basically starting to push back on the CSRD, primarily because if you remember back to my slide where I was talking about if you go too far in on sustainability without a thought on how it impacts things, you start to deindustrialize economies and you start to make yourself less competitive. So right now there's pushback on this in Europe, wanting to reevaluate how this rolls out. So again, it's important to understand the politics and the policy behind all of this because it can change very, very quickly. And you may think that, well, I'm not in Europe, I'm not in the UK, the US didn't pass this, it doesn't apply to me. Well, if you're selling into Europe, as long as the CSRD is in place, if you're selling to brands that then sell into Europe, you'll have to report your emissions to the brands as part of doing business with them. So for those of you who aren't familiar with Scope 1, 2, and 3, just a quick graph that kind of shows what it is. Scope 1 on the far left is the emissions that your plant releases to atmosphere. Scope 1 was established in 2004. Scope 2 is your purchase power. So it's all of the greenhouse gas emissions related to that purchase power for your facility. And then Scope 3 is the supply chain up and down. And that was established in 2011. But like myself, and probably many of you, it probably was only about 4 or 5 years ago that I even started hearing about any of these initiatives. And that's because the policy started rolling into financial reporting, and that's when it became relevant. That box there on the corner or on the right side shows you all of your greenhouse gases. And it's important to note that water vapor is the single biggest greenhouse gas. They haven't tried to start regulating that yet. They focus on carbon dioxide because of the 10 that are listed. Carbon dioxide is the greatest concentration, followed by methane and nitrous oxide. So methane comes into play when they start regulating cows. You know, when cows emit methane, as well as nitrous oxide that's in fertilizers. So when you start to understand this, you can see what's driving a lot of the policy. Quick timeline on Hotmelt, and then we'll get into pressure-sensitive adhesives. Hotmelt is not a new technology. Rubber-based Hotmelt was developed in the 40s. Procter & Gamble was an early player, as well as Nordson Corporation for the dispensing of it. So Hotmelt developed in the 40s. It really gained traction in the 60s, where it started being used in a lot of packaging applications. In the 80s, kind of starting to really embrace the Clean Air Act, they started looking for different technologies to reduce air pollution and do things at a lower application temperature. And so UV acrylic Hotmelt was actually developed in Japan in the 80s and promoted for those two reasons, right? To reduce emissions and support of clean air regulations globally, as well as to produce a technology that would allow you to apply adhesives at lower application temperatures. In the 90s is when UV acrylic Hotmelt commercializes, predominantly, again, to address, clean air, reduce emissions. But what also was happening at the same time is we really started to see an uptick of globalization, and the big polluters really just offshored production predominantly to Asia. So instead of addressing it, we just moved it. The pollution didn't go away. It just went to a different part of the world. Starting in 2000s is when all the sustainability policy starts to come along. At the time, UV acrylic Hotmelt, single-digit market share, right? But as companies start to get more, a better understanding of and started to make these global pledges to how they were going to become more sustainable, how they were going to become more efficient, you're starting to see more and more people look at UV acrylic Hotmelt as a way to meet those sustainability targets, but by also doing things more cost effectively and still allowing them to produce production. And then in the 2020s, which is kind of where we're at now, you're starting to see companies bring back production, expand production. They're having to comply with scope emissions reporting. We're all facing rising energy costs. That's not going away anytime soon. I mean, we're looking at another 5 to 10 years of increasing energy costs. And then those initiatives, clean air initiatives, sustainable initiatives, they're now global. Like, you can't just move a plant somewhere where regulations are less strict. I mean, if you're a global brand and you're making sustainability pledges, even if local regulations don't force you to do something, because you promoted it as part of your goals and your targets, you're going to be implementing more efficient processes regardless of where those plants are located. So now if we move on to pressure sensitive adhesives, just to kind of give you kind of an overview of what they are. Pressure sensitive adhesives, or PSAs, they're always tacky, right? And it's an adhesive, it's sticky. It's designed to flow out and stick when light pressure is applied. The end use product, right, that adhesive that you're using, and we'll talk a little bit about the different types of adhesives, but you're going to select that product based on the degree of tack or shear properties, as well. How long that adhesive is going to last is going to depend on the mating surface properties, as well as the degree of surface contamination. So not all adhesives are PSAs, and UV PSAs in particular can come in two forms. We have lower viscosity formulations. You'll often hear these referred to as liquid or syrup adhesives, or liquid PSAs or syrup PSAs. And those are going to be applied during your typical like Flexo or Gravure application process. So if you're already using Flexo or Gravure, there's no additional equipment investment. You would just put a UV PSA, low viscosity, in your machine and apply it the way you are normally applying it. It has some performance limitations, but doesn't require any additional equipment. What we're going to be talking about today is the higher viscosity formulations called Hotmelt, and those are going to be applied via slot die. So it does require investment in equipment specific to the ability to apply UV Hotmelt. So pressure sensitive adhesives, some of the properties we'll often talk about is the tack, which is the stickiness. It's how well an adhesive bonds to a mating surface when applied with pressure. Cohesion is the internal strength, right? How is that adhesive? Because it's flowing, right? So how is the adhesive bonding to itself? Is it able to resist stretching, tearing, and does it break under a given load? Adhesion is that bond with a mating surface. How well do those molecules interact at a microscopic level? So if you look at the graphics there, the cohesion is what's going to determine the shear strength, the shrinkage, whereas adhesion is going to give us more of the tack and the peel strength. And if you look at the graphic on the far right, the top part of that shows an adhesion failure, right? Where the top substrate just doesn't stick, right? There's nothing to hold it in place, so it separates. Whereas a cohesion failure on the lower image shows where that adhesive itself just failed. It couldn't hold itself, the integrity of it couldn't hold itself together, and so it was the failure mechanism. So for UV acrylic hot melt, the interesting thing that makes UV very appealing to a lot of people is depending on how much UV you apply, more or less, you can affect the shear and the tack properties, right? So if I give it more UV, my shear strength gets better. If I give it less UV, my tack gets better. So one of the beautiful aspects of UV acrylic hot melt is for a given line, depending on how much UV I'm applying at a given time, I can produce a different product. So with one adhesive SKU, I can produce a wider range of products for the different portfolio that I'm offering my customer base. The applications where PSAs are used are wide-ranging. They're in removable labels, both pressure-sensitive labels and linerless, permanent labels, resealable packaging, tapes, graphics. You can find it in industrial and automotive components. So medical devices, a lot of your dermal patches, building materials, so roofing products, flooring products. It's quite diverse where pressure-sensitive applications could utilize UV hot melt. It's important to note that they're generally food and skin contact safe, and that's because they have a very high molecular weight. But it's always important to consult with your adhesive supplier to be sure. So when we look at pressure-sensitive adhesives, there's generally 4 types. You can have water-based, also referred to as like an aqueous dispersion. A water-based adhesive is going to use water as the carrier. So the tacky part of the adhesive is applied through the use of the water. So the water carries it onto the web, and then you have to evaporate the water. It's important to note that water-based materials are always promoted as the most sustainable, but what people fail to realize is that it takes an awful lot of energy to evaporate water off of a substrate. So while the cost of the raw material might be lower compared to the others, you have to look at how much energy, the coat weight you're applying, and how much energy you're applying to evaporate it. Solvent-based adhesive is similar in that we're using a solvent as the carrier. So all of the adhesive components, we dilute them in the solvent so that the solvent allows the adhesive to be applied. And then we have to evaporate that solvent off. And while it takes less energy than a water-based material, you often then have to incinerate those solvents before you release that air to the atmosphere. The third one on the list is a rubber-based hot melt. So rubber-based hot melts are a heat set technology. So we heat this hot melt up to apply it. And then once applied, we got to cool it back down. And as long as it's cool, it's going to give you the tack and the shear properties that it's designed to do. But if you reheat it, it's going to flow again and will cause your substrates or whatever you're holding in place to become misaligned or potentially fail. So rubber-based hot melts are going to have limitations in extreme environments. And then we've got the UV acrylic hot melt. So UV acrylic hot melt is manufactured in the same way that a solvent-based adhesive is manufactured, but the manufacturers pull that solvent out immediately before shipping to the converter. So what you receive is a higher viscosity adhesive, raw material, or something that might even be more of a solid block. You have to heat that up to then apply it to your web, but there are no solvents, which makes it much more sustainable. And it also allows the manufacturer, when they strip those solvents, to recycle them and use them with the next batch of adhesive that they manufacture. So how is hot melt applied to a web? Well, you've got the bulk hot melt on the left. It could be more of a rigid hot melt like you see there, or it could just be a higher viscosity liquid-like substance. You're going to receive that either in a drum or a pail. So you've got a drum and a pail unloader in that second image. That is meant to heat the hot melt up to the application temperature. You can either pump it directly from the unloader to the slot die on the far right, or you can have an intermediate station, which is the melt tank. The advantage of the melt tank is that it takes a couple hours often to heat this hot melt up from room temperature. And so if you use a melt tank, you can pump to the melt tank, and the melt tank will supply the slot die on the far right, while you can insert a new pail or a new barrel to heat up. And so you've got that intermediate supply that you can continue to deplete while you're heating up the next drum or the next pail. The far right is the slot die. As you can see, it's not a flexo station. It's not a gravure station. It is literally a slot, and you can control the thickness of that slot. And we're basically going to take the hot melt from either the unloader or the melt tank through a heated hose that feeds that slot die and then pushes it out onto the web. Typical UV hot melt coat weights. In the US, we tend to refer to mils. In Europe, they tend to refer to GSM. You can convert between the two. 1 mil is about 23.74 GSM. I typically use 25 GSM to convert. It just makes it a little easier. So on the top graph, you can see it's in mils. The lower one is in GSM. They're basically the same. The purpose of this image is to kind of communicate the difference between free radical and cationic. So free radical means that the adhesive needs to see the UV in order to react. Cationic uses the UV to initiate the reaction. Once it leaves the light, it's going to continue to react and may take a period, and will always take a period of time to go to termination. So cationic materials can take anywhere from a couple hours to a few days to fully react, whereas free radical are fully reacted once they go through the UV light source. If you're using thicker coat weights, that is when you're going to have to go with cationic. Free radical has a limitation on the thickness of the adhesive that it can penetrate. So typically, if you're between 0 and 4 mils, that's when you're going to use a free radical. Kind of in that 4 to 7 mils, you could probably use either. You definitely should consult with your adhesive supplier. But once you get above 7 mils, as you get into more of those building and construction, projects, you might want to look at a cationic material. To avoid contamination, if you are using a range of coat weights and you're going to need to use both free radical and cationic, you're going to want to have dedicated unloaders, melt tanks, and hoses, because you will contaminate if you're using the same material. It's too difficult to clean them properly to prevent that contamination. So here's a diagram of what a UV acrylic hot melt process looks like. On the far left, you see that drum unloader. From the drum unloader, we're going to go to the melt tank. And then from the melt tank, we're going to the slot die. The slot die is positioned over a chilled roller. The base substrate is going to unwind here from the bottom. The web is going to pass over the chilled roller where the adhesive is applied, and then it immediately goes under the UV lamps. Those lamps can be positioned over a chill plate or a chilled roller. And that chill plate or that chilled roller is primarily there for the UV systems. It's meant to capture the stray energy that doesn't go into the reaction. It's also helping start to cool that adhesive down a little bit. Once it comes out on the UV systems, it's going to go through a nip roller where the release liner then is applied. They're nipped together and then rewound here on the far right. So there's different variations of this. You can have different number of lamps. You can have different types of components. You can have a different web path. But this should give you a basic understanding of what that UV acrylic hot melt process looks like. And then if we put this, imagine that same process then put into a production line. All those components are represented here. On the far left where it says number 1, you're going to unwind that base substrate. It's going to go underneath here and up under the slot die, which is number 2 on a chilled roller. It's going to go up to number 3, which is where you see 3 UV curing systems on a chilled roller. On the far right, we're going to unwind the liner, which it's not the web's not shown here in the illustration, but it's going to come up over the top. It's going to snake down, and it's going to be laminated just after number 5, just after the UV station. And then it's going to be rewound on station 6, where you're going to have the fully laminated product. This is an illustration that's courtesy of Valco Melton. I've got another one here from Elite Cameron. Basically the exact same setup, just laid out a little bit differently. The important note on this one is that this whole line from start to finish is only 32 feet long by 18 foot wide, and it runs a 63-inch web. So one big advantage of UV hot melt is that because you don't have those long tunnel dryers, we don't need to evaporate water. We don't need to evaporate solvents. We don't need a series of chilled rollers to cool down the rubber-based hot melt. The line becomes much shorter. So if you're already running PSAs in your facility and you want to add additional line because you've run out of capacity, you don't need as much space to put in another line. And that's what's being very, one of the reasons UV hot melt is very attractive to a lot of companies, is it just takes up less floor space. I'm not going to read this. I think it's everything I've been saying is kind of just put together here in this nice little table, right? On the left, we've got all the features, no solvents, a lower melt application temperature for UV acrylic hot melt compared to rubber-based hot melt, the ability to change the UV output to adjust tack and shear. It's all electric operation, no hydrocarbons, 100% solids. It doesn't emit my greenhouse gases, my volatile organic compounds, my hazardous air pollutants, my toxic air pollutants, my fog. So fog is when components come off of plastics and adhesives and coatings and then deposit on the inside of like windows and inside a car or places where you don't want them to build up a film. So we've got all these different features. And on the right, they translate into the benefits of the converter, right? Safer environments, less shipping, reduced scope 1, 2, 3 emissions, less floor space. All of this together is a very appealing case for UV hot melt. But with the exception of scope 1, 2, and 3 emissions, all of these features and benefits existed in the 90s, right? They haven't changed. If I had done this presentation in the 90s with the exception of the scope emissions, I would have given you the exact same table. So why is it that UV hot melt has held single-digit market share since its inception? Why is it that we haven't had more adoption if it makes such a compelling case? Well, features and benefits, if they don't solve a problem, they have no value. And this is, a lot of companies will promote their features and the benefits of the products that they're offering, and they just expect people to agree and say, that's exactly what I want, sign me up. But unless you take those features and benefits and you translate that so the customer understands the problems it's solving, then they have no value, right? Features are the characteristics and capabilities. Benefits are the positive effects. But I can have great characteristics and great positive effects, but if it's not solving problems for me as a converter, I don't really care. And so because UV hot melt was designed to reduce emissions, to help air quality, right, to allow it to be applied to more thermally sensitive substrates, if I found other ways to do that, or I could have just moved my production, my pollution causing production overseas, then all of a sudden I didn't have a problem that needed to be solved. And UV acrylic hot melt was just looked at as an alternative that had some great features and benefits, but didn't really solve a problem. So what's changed? Well, sustainability has changed. There are many external market pressures, environmental social governments, that whole environmental aspect that we've been talking about, the increase of regulation, scope 1, 2, and 3 emissions, requirements in UK and Europe to report your sustainability, your emissions on your financial reports. Again, that's 50,000 companies in Europe, 11,000 in the UK, and all the companies that are supplying those brands. We've also got rising energy costs. Everything that we've been doing to try to create a green grid has just driven up energy costs, right? Solar and wind, I've given presentations on this. They are responsible for driving up energy costs because they're very difficult to balance on the grid. And we've overinvested the last 20, 25 years in solar and wind, and we've underinvested in dispatchable power. So energy costs are going up. It's going to take about 5 to 10 years to correct this. So that's not going away anytime soon. We've also seen the demand that data centers and AI are putting on. So not only did we not properly plan for the future, we have this new technology that for some reason nobody calculated into what was really required in terms of energy. So costs are going to be high for the next 5 to 10 years. And then we've got increasing compliance demands. So what that means is if you look at the image on the bottom there, that graph I showed you originally with features and benefits, all of a sudden they start to overlap a lot more, right? Now I've got sustainability problems that UV acrylic hot melt is solving. So that value increases, right? I'm eliminating solvents. I'm eliminating scope 1 emissions. I'm reducing scope 2 and 3 emissions. It's all electric, reduced operating costs, lower footprint. I mean, all those aspects from that table all of a sudden can be translated to sustainability. The value goes up, and now all of a sudden you have interest in a technology that was developed in the 80s that is now the perfect solution for today's problems. So now we're going to get into UV terminology, UV technology, and how you match UV to a UV hot melt line. So these four terms, wavelength, irradiance or intensity, energy density or dose, and electrical power, are what UV equipment suppliers will review when selecting the appropriate UV system for an application. So wavelength is the distance between two corresponding points in a wave. So UV output spans between 100 nanometers and 450 nanometers. That's the part of the electromagnetic spectrum. If we go to shorter wavelengths, we end up with gamma rays and X-rays. And if we go to longer wavelengths, we get to visible light, infrared energy, and then, radio frequencies, AM, FM, microwave. But we're in the UV range. So it's 100 to 450 nanometers. To give you kind of context of what that means, a sheet of paper is 100,000 nanometers thick. So that the wavelength, the distance between those peaks for UV wavelength is very, very, very tiny. Irradiance, more often called intensity, is watts per square centimeter. And a watt is a joule per second. So I can also write that as joule per square centimeter per second. It's energy per area per time. It's the rate that I'm delivering energy to the substrate. If you've got familiarity with UV systems, you know that the power level of the UV system, how powerful of a system I buy, is going to determine how quickly I can deliver those photons of light to the substrate. And we refer to that as intensity. The energy density or dose is the intensity over time, right? So if I've got intensity as joule per square centimeter per second, if I integrate that over time, I'm left with joules per square centimeter. So that's energy per area. And with UV hot melt, that is what we're most concerned about, the total energy to set that adhesive. And by varying that quantity, I can increase or decrease the tack and the shear. The bottom one is electrical power. That was terminology that was created by General Electric in the 1930s. It just refers to the energy going into the system. So it's input power divided by length of lamp. It doesn't tell us what's coming out. Arc lamps, for the most part, if we talk about the watts per centimeter, watts per inch, it kind of gives you a general understanding of what level of power it has. But what we really care about is the wavelength, irradiance, and energy density. And for the purposes of UV acrylic hot melt, what's most important, they're all important, but what's most important is going to be the energy density or the dose. So this schematic or graph shows us the bands. So we can take ultraviolet light and we can break it into 5 bands. On the far left, we've got the shortest wavelength, which is vacuum UV. It has the most energy, but it's completely absorbed by oxygen. So unless you're running in a nitrogen environment, the vacuum UV wavelengths do not even reach the substrate. UVC is absorbed at the surface. It also has a lot of power, but it doesn't have the ability to penetrate very deep into the adhesive. UVB goes a bit deeper, UVA goes even further, and then UVV, which is on the visible, just starts to cross over to the visible range, penetrates very deeply, has less energy in comparison to the other bands. With UV acrylic hot melt, we're mostly focused on UVC, and that's primarily because the chemistry that's been evolving since the 80s is designed to react to those UVC wavelengths. They've got a lot of energy. They may not penetrate very deep, but once they're absorbed by the photoinitiators and adhesive, the reaction will continue to propagate. And as long as we're below, 4 to 7 mils, a standard free radical chemistry is going to be fine. Once you start to get to those thicker coat weights, 7 mils and greater, that's when we like to switch to cationic because it just tends to penetrate those thicker coat weights much, much better. Formulators will specify the UVC energy needed to react to hot melt in the units of millijoules per square centimeter. So that's the dose of UVC per GSM. So when I'm working with end users, when I'm working with OEMs, when I'm working with formulators, that is what we need to understand is how much energy per coat weight do you need to react adhesive? What coat weight ranges are you targeting? And then how fast do you need the web to run? If we look at how irradiance and energy relate to each other, this is a static irradiance profile. So on the y-axis, we have irradiance, and on the x-axis we have time. So if I had a box with a UV system in it, and I could put my sample in that box and close the door and turn that UV system on from time 0, the irradiance would spike to the top of that square. And that irradiance would stay constant until I turn the light off. If that was my application, I could take my irradiance and multiply it by time, and I would know my energy density, right? Very, very simple, very straightforward. However, on a web, on a converting line, we've got a dynamic irradiance profile. As the web and the adhesive approaches the UV system, the irradiance, peak irradiance, again, the rate of energy delivery, gets faster and higher and greater until I reach the center of the lamp, where it's the peak of this bell curve. That's where my irradiance is the highest. And then as the web moves away, that irradiance, that peak, falls off to the end. So a lot harder to calculate. We typically try to measure these values and extrapolate the values for the different applications, because the dose is the energy under that bell curve. And for those of you who've got a lot of experience in calculus and like to run those calculations, it is possible, but we tend to, it's easier just to measure it and then extrapolate out. So if we look at a theoretical application where I've got 3 arc lamps, arc lamp 1, 2, and 3 reading left to right. And if I set the power of lamp 1 to 100%, lamp 2 to 100%, and lamp 3 to 50%. And yes, I used very, very easy numbers because it just makes it easier to explain, but I could have set them to anything. You can see that dynamic profile of irradiance. It's that purple line. Y is the peak irradiance, and then A represents the area under the curve. So if I run a web sequentially under lamps 1, 2, and 3, when it goes under lamp 1, it's going to hit peak irradiance of Y, and it's going to get dose of A. When it goes to lamp 2, it's also going to see irradiance Y and dose of A, but dose is additive, right? So now I've got the combined dose of A plus A, but my intensity for both situations is not additive. It's strictly Y. I go to that third lamp that's running at 50% power. So now my intensity is cut in half. So it's Y over 2. My dose is also cut in half because that area is now A over 2. So if I add them together, I experienced intensity Y at lamp 1, intensity Y at lamp 2, and Y over 2 for lamp 3. But my dose is the summation of all 3 lamps. So basically I get 2.5 A. And so by adjusting the dose is how we're able to adjust the tack and the shear for a given UV hot melt adhesive. If I increase my web speed for these 3 lamps, powered exactly as you see there, if I double my web speed, so I'm under the lamps for less time, my intensity doesn't change, but now my dose is cut in half because I went faster, right? If I go twice as fast, my dose is cut in half. By the same fashion, if I slow my web speed, if I cut my web speed in half, again, the intensity doesn't change, but I now double my dose. And that's how we can control the UV output for a wide range of products. So specifying UV hot melt for PSA lines, you can have anywhere from 1 to 8 lamp heads. It really depends on what you're trying to do, how fast you're trying to do, the range of coat weights. My advice to people is don't try to do everything. Typically, you want to stay within a couple mils. You might want to do a 0.5 mil to 3 mil, or 3 mil to 7 mil. But if you come to me and say, I want to run everything from a 0.5 mil to 15 mil, and I want to do everything at 1,000 feet a minute, you're going to end up with a ridiculously high number of lamps on your line. And while I'm happy to sell you those lamps, it is you won't be using most of them, and it's a waste of money. So anytime we embark on a new hot melt line, we want to narrow the scope. Realistically, what coat weights are you going to run? Typically within, probably 2, 3, 5 mil variation tops. And what speeds do you want to run? Because what I can also do is as I run thicker coat weights, I'm just going to slow my speed. So I don't have to necessarily double my lamp heads. I'm just going to run a bit slower for the applications where I have thicker coat weights. UV hot melt only relax to UVC. So this is why you do not see any commercial LED formulations today. They're in development, but they're not commercial today. We always make the arc lamp about 10 centimeters or 4 inches wider than the max coat width. On an arc lamp, you lose a little bit of UV output at the ends. They kind of fall off. And because we want uniformity of tack and shear across that web, we're going to make the lamp head 2 inches longer on each side. We like to mount the lamps around a chilled roller. We can also do a straight through web path. The images on the right, the photos, the upper one shows you 3 lamps mounted around a chilled roller, and also has a dummy spot in case we wanted to add a 4th lamp later. The system on the bottom is a straight through web path. So the web will go in between that heat sink on the bottom and then underneath the lamps. And when the web is running, that hinge would close shut. So you'd have a very tiny gap between the heat sink and the lamps, just enough to let the web pass. The UVC energy density must match the required hot melt energy density needs. Again, this is why understanding your coat weight needs and your web speed and the adhesive that you're using are incredibly important, because we need more of it the faster you go and for the thicker coat weights. So this is a table of a typical UV arc lamp. So the headers for each of the columns are UVA, UVB, UVC, UVV. Again, what we're most concerned about for UV hot melt is UVC. If we were running inks, we'd be more concerned with UVA. All of these wavelengths factor in the reaction, but we tend to focus on the one that's the most beneficial for the way the chemistry was formulated. So with UV hot melt, that is UVC. So the top row is energy density. Second row is irradiance. And then the third row just shows you the contribution as a percentage of the total. So this particular arc lamp was 180 watts per centimeter, 457 watts per inch. It was measured for a web speed of 120 meters per minute, which is about 400 feet a minute. On the next slide, I'm going to show you I'm increasing the power of the lamp. I'm going to go from 180 to, I think it was 220. And I'm taking the web speed from 120 down to 60 meters per minute. So you can see that 15 that I've got circled there, it increases to 39. So that's just by kicking the power up and cutting the web speed in half. Again, I go from 15 to 39. And so these are the calculations. They're not difficult, but you have to understand what the UV source is emitting. And then you have to calculate based on the adhesive you're using to figure out exactly what the energy is required to give you the properties you want. And so how do we do that in practice, right? So let's just kind of look at a more detailed example. So let's say I've got a particular UV hot melt and it requires an UVC output of 1.2 millijoules per square centimeter of UVC per GSM to cure. I can calculate that from 0.5 mil up to 5 mils. And for each of those mil specs, if I multiply that by each mil being 25 GSM, I can translate that to GSM. And then I'm going to multiply that by 1.2 millijoules per square centimeter. That tells me how much millijoules of UVC I need to run 0.5 mil, 1, 2, 3, 4, and 5. If I take my 120 centimeter arc lamp running at 220 watts per centimeter and 60 meters per minute, which is 200 feet per minute, the dose is additive. So if I have 1 lamp, I've got 39. If I take 2 lamps, it doubles. If I take 3 lamps, it's 3 times a single lamp. So you can see how that output of UV lamp increases as I add lamps. And now if I double the speed, if I go from 200 feet a minute to 400 feet a minute, that dose is then cut in half. So it's very easy. And what we do is we create an Excel spreadsheet that allows you to calculate this very easily. There's also ways to measure this in real time online, which is what most people prefer. So I can take a range, right? So now if I'm looking at lamp quantity versus coat weight versus speed, I might say for 2 lamps, I can run 0.5 mil at 1,000 feet a minute. But if I increase that coat weight to 2 mil, now I need 3 lamps and I'm going to cut my speed down to 400. But if I want to go faster and I still want to run 2 mil, then I'm going to need 6 lamps. And equally, if I want to go even thicker in coat weight, 6 lamps to run 4 mil. So converters that understand this can run a wide range of applications with a single adhesive SKU by just varying the UV output. It's important to know that lamps vary in nominal output. So I happen to use a 220 watt per centimeter lamp, but they can range anywhere from 130 to 240. So if I had a lower powered lamp, I'm going to either need more lamps or I'm going to need to run slower. So how do we monitor UV output in real time, right? Like you may say, Jen, you just showed me all these calculations and my operators can't handle that. That is way too complicated. I'm going to stick with my water-based adhesives and my solvent-based adhesives and call it a day. And that's understandable. But we do want to make the process easier for you. So there are a couple ways to measure in this process to take the guesswork out of it and make your system a little bit more automated. On the top left is an example of a system that might just measure the intensity. It's not measuring dose, but it is going to measure the intensity, and it's going to give you an idea of how that lamp is degrading over time. The image on the bottom left corner, that's a radiometer. You can pass a radiometer, can't pass it through a chilled roller, but if you have a straight through web path or a lab setup, we can run the puck radiometer, and it's going to measure that intensity for UVA, B, C, and V, and it's going to do that mathematical calculation to give you the area under the curve, which is the dose. Or the image on the right, and we're starting to see a lot more of this being used in application, is you've got a scanning system. And about every 10 minutes, the scan is going to take a scan of the lamps, going to measure the intensity, and calculate the dose. And so each lamp would have a scanning system. And what you could do is on the HMI, you would input the target dose for the product you're running. It doesn't know the coat weight, doesn't, know the performance properties. You have to tell it the dose that you want to hit, and it's going to do based on the web speeds that you're running, and you can vary the web speed. It's going to adjust the power of the lamps on that line to give you that targeted dose. So just in conclusion here, we're just about 5, 6, 7 minutes left. What's happening is UV acrylic hot melt is finally getting its due, right? It's always been a great technology. It's always been very versatile. And it solved a lot of problems, but they were problems that nobody cared about, right? If energy costs are cheap, and if I can just move my manufacturing plant to a country that doesn't care as much about pollution or isn't in a position to regulate it, then you didn't need UV hot melt. I'm just going to stick with my water-based adhesives and use a lot of energy to evaporate that water, or I'm going to go solvent, and depending where I'm operating, I'll either incinerate it or I won't. And then I'll use UV hot melt where it makes sense. But UV acrylic hot melt, single-digit market share until now. And I can tell you that we are seeing a massive uptick because companies are not going to stop running adhesives. Adhesives are so versatile. If you remember that slide in the application, they're used in everything from labels to medical device to building construction and everything in between. UV acrylic hot melt allows you to do that in a much smaller footprint to give you a wider controllable range of properties with a single SKU. So now you're warehousing less adhesives, and you can do it in a much more environmentally conscious manner, right? There's no solvents, there's no afterburners, there's no oxidizers, reduced amount of energy. I don't have those long tunnel dryers. I'm not using that tunnel dryer to evaporate either a water solvent, but it's also not heating up my plant, right? Which is taxing my HVAC system. And again, sucking in energy in different ways. So as brands and converters are running rapidly approaching deadlines to meet previously pledged sustainability targets. Again, a lot of these targets were pledged 5 years ago, 10 years ago, and they were always way in the future. Well, that future is pretty much here now for many companies. Some companies had 2025 targets, others have 2030 targets, others are 2035. But what they're discovering is UV acrylic hot melt's an established and proven solution. And so sustainability is giving it a newfound purpose. So with that, I will conclude my presentation. I think we've got about 5 minutes left for questions if anybody happens to have any.
Thank you, Jennifer. Great presentation. Really appreciate it. And we do have a couple questions. Have time for a couple. One of the questions that came into you was, if a converter doesn't currently use UV hot melt, what steps can they take to get more information in order to see if it's a fit for their product? Sure.
So I always recommend to start, if you're a current converter of PSAs, always start with your incumbent adhesive supplier. All right. So whoever you're using today, you just ask your representative if they also offer UV acrylic hot melt, kind of get a take on what their offering is. A lot of your hot melt adhesive suppliers have pilot lines in their development facilities. Some are in a position to run samples. If your current supplier does not offer UV hot melt, by all means, give me a call. I can certainly put you in contact with people. And then certainly give me a call as well, because I can at least take a look at what your existing converting line is, and if it's something that we could retrofit, or if you're looking at a new line, maybe that's outside your budget at present day, but it may be that we can actually put lamps on your current line so that you could continue to run what you're currently doing, and then also experiment with UV hot melt to see if it's a good fit, and then expand as you get more comfortable with it.
Another quick question is, how do you see the integration of Hotmelt and Flexo narrow web presses?
So with narrow web, you can put a UV hot melt station on one of the Flexo stations, right? You can put it in place of your typical Flexo. It will be a dedicated station. That slot die, in the drum and loader or pail and loader is not something that you're going to be wanting to swap in and out. So it's going to be a dedicated station. And you would basically buy the UV system for that web width. And depending on the narrow web press, you will be limited to how many lamps you can put on there. But typical narrow web presses don't run faster than 1,000 feet a minute. Some can, but for the most part, they run less than 1,000. So if you only have room for one lamp, that's going to dictate the fastest speed or the coat weights that you can run. But for most narrow web applications, that's probably fine. You're not running building products, building instruction materials where you need, a 10 mil, 15 mil coat weight. You probably only need a half a mil. And, for a half mil application, with one or two lamps, you're going to definitely clear the speeds for narrow web Flexo. We saw after the pandemic, a lot of suppliers got caught out where they couldn't get, a lot of, printers got caught out and they couldn't get their supply material. So you started to see a lot of interest of people wanting to bring that in-house. So we're seeing, silicone release, UV acrylic hot melt being integrated into narrow web Flexo presses, because now they can do all that in line and they can better control their processes, being, at the mercy of their vendors at the, for that particular product. So I think there's opportunities there. It's probably not a fit for everybody, but it does give you a lot more capability on a narrow web Flexo press.
Great. And time for maybe one more on that subject, and Tom with Telstar had made a comment that they do have a pattern hot melt printer for narrow web that's available.
Very good. Yeah.
Yeah.
Absolutely. Yeah, Telstar makes a great product. And I think that's what's important, right? Is identify the suppliers, right? Have conversations. Talk to Tom at Telstar, talk to the other, OEMs, talk to me, talk to adhesive suppliers. Companies are doing this with UV hot melt and narrow web and mid web and wide web. And we're seeing that grow all because of these sustainability pressures that are in the marketplace. So have those conversations. There's no need to reinvent the wheel. Talk to people who are already doing it right now.
Great. There's a couple other questions, but we're really pretty much out of time. And what I would suggest is it's great that people are very interested in this, Jennifer. Please reach out. You can see Jennifer's email and phone number on the screen there. So feel free to reach out to her. And Jennifer, thank you again for putting on this webinar. It was very educational, and we appreciate your time.
Thank you very much.
Thank you.